So red blood cells are, so macrophages are eating the red blood cells? They are. But a red blood cell is almost exclusively hemoglobins. After it ejects its nucleus and organelles, there's almost no cytoplasm in there. It's just a membrane-bound sac of 250 million hemoglobins. So on this picture, they're trying to show us what happens to all those 250 million hemoglobins when a single red blood cell is eaten. And they're eaten by the millions every day. What happens to all this hemoglobin? Well, in short, most of the hemoglobin is recycled. So I want you to see it gets broken down into those globin chains. Remember those lighter brown and darker brown strands, the 2 alpha subunits and 2 beta subunits? Those globins get broken down into their individual amino acids, and those amino acids are completely reusable. They're completely recyclable. Those amino acids just get released out into your bloodstream, and now they're just a nutrient like you might get from eating a hamburger. They're just amino acids available now to any of your cells to use as a nutrient. So the amino acids that were making up those globins, wait, let me remind you of the globins are these brown chains of amino acids here, right? 2 alpha, 2 beta. Those globins are just going to get recycled. The amino acids get reused. But the heme group, here's what happens in the heme group. The heme group, part of it's going to get recycled, and part of it becomes waste product. Remember the heme included that green iron in the middle? Well, the iron is completely reusable. So we're going to remove the iron, and we store it up in the liver. You may already know that the liver is the iron storage organ in the body. It's one of the reasons people like to eat liver meat, because it's one of the richest sources of iron a human being. I know people don't like to eat it, but if you doctor it up with onions properly. I used to order it on the menu at Friendly's, where it was on the senior menu, and I had to convince them to let me order from the senior menu, because it's not on the menu otherwise. But it's really, really rich in iron. Now there is also a whole bunch of toxic crap stored in the liver, and you're getting that too when you eat liver meat. But it's good if you like the onions. The iron is completely recycled. The amino acids of the globins are completely recycled. Wait, what do you mean recycle the iron? We store it in the liver, and then later when we're doing erythropoiesis and we have to make new hemes and make new hemoglobins, we're going to need iron to build new red blood cells later. So we store the iron in the liver and we use it for later. Okay, but then the rest of that heme group, when you remove that green iron out of the middle, well, all that red organic chemistry around the edge, all of this red stuff here, with the iron removed, is known by the somewhat famous name bilirubin. Maybe you've heard of bilirubin before. It's the heme group minus the iron. The bilirubin is a waste product that has to be removed from the body. Wait, let me go to the blown up. The bilirubin has to be removed from the body. And the bilirubin is going to get out of your body through a very unconventional route. It's going to leave in the poop. But very few things would ever leave through that route. I'm desperate to try to convince students that your body only makes very few waste products. The cells make CO2 as a waste product, and that leaves the body through the lungs. We exhale CO2. The body makes those nitrogenous wastes that you might have to list from me on today's quiz: urea, uric acid, ammonia, and creatinine. And those leave the body in the urine, right? Removed from your bloodstream by the kidneys, and then incorporated into urine, and we pee those out. That is almost the complete list of waste products produced in the body. Here's an exception. Here's an additional one. Bilirubin is a waste product that does not leave through your lungs or through your kidneys. The bilirubin leaves through the digestive tract and leaves in the poop. And the way that bilirubin leaves is a story in itself. The bilirubin is incorporated by the liver into a substance that the liver is busy making that has nothing at all to do with bilirubin. The bilirubin is incorporated into an unrelated substance that you've heard of before called bile. Bile has nothing to do with this story. Bile is produced by your liver to help you digest fatty foods. The liver makes bile, and you're not always eating fatty food, so when it makes it and there's extra, we store it up in that little gallbladder that looks green underneath there. That's for storing up bile. And then when you eat a big value meal, like I'll take a number 5, like that. When you eat like a big value meal, it's got 38 grams of saturated fat in there. Then like your gallbladder squeezes, you get a whole bunch of bile, goes out into the lumen of your intestines to help digest your fats. We'll get to this with the digestive system. Bile is a digestive product produced by the liver for the sake of digesting fatty substances. It has nothing to do with bilirubin. The bilirubin is incorporated in the bile as a stowaway. It's just hidden inside of the substance called bile. The bilirubin has nothing to do with bile's function. It's just going to co-opt this route out of the body for us to get rid of it. So then when you eat some fatty foods and the liver gallbladder system releases bile out into the lumen of your intestines, now that bilirubin is out there in the bile, out there in the lumen of your intestines. And then when there are undigested foodstuffs that are going to leave your body as feces, there's also some bile that's leaving too, and that brings the bilirubin out of the body. I used to draw a little toilet bowl over here to show you that the ultimate fate of the bilirubin is that you're going to flush it down the toilet. It's the only waste product that you get from the dying, aged, dead red blood cells that are getting eaten up by macrophages, because these other parts get recycled. I'm trying to convince you. What happens to bilirubin? You flush it down the toilet. Now wait, beware of figure 17.7, because I didn't talk about some of the things that are down here, because they're trying to use this picture to tell you a different story. They're trying to use this picture to tell you where do you get all the raw materials for building red blood cells to begin with. And I thought they were taking on too much with this picture to incorporate that into here also. And that just doesn't happen to be on any list of what we have to know. So I'm not talking about number 6 here at all. That's why I try to get this picture to steer over to a different end, the toilet bowl over there, so we don't get distracted by extraneous information. Everybody feel like they know what happens to red blood cells after they've worked for 100 or 120 years? Eaten by macrophages, most of the parts are reused, recycled, but bilirubin has to be removed. Okay, what else do we have to talk about here? Well, it seems to fit in my mind under the topic of red blood cells. This picture 17.8, we're not going to talk about. But its presence in the chapter helps to remind me something. Look, some people have a genetic disorder called sickle cell anemia, where the red blood cells take on this shape instead of this shape. Healthy red blood cell, as you know, sickled red blood cell, which you may have never seen before. What causes red blood cell to take on that shape? Oh, look, a single amino acid substitution in the long chain of amino acids in the globin. So, you know those globins, those chains? If you have a genetic disorder that instructs your ribosomes to put the wrong amino acid in this spot, then it changes the entire structure of the hemoglobin, so much so that it changes the entire shape of your red blood cells, and now you got this. And this is one of those places where I like to remind you of that picture I drew you of a really narrow blood vessel where the red blood cell is wider than the blood vessel itself. Imagine this cell now in that tiny, tiny narrow capillary. It literally, the jagged edges literally they stab into the wall, and they get stuck in the wall, and they cause a traffic jam. And then downstream tissues are going to suffocate the starve. It happens all the time.
Is that traffic jam like a blood clot or something?
A blood clot's a little bit different thing. But that traffic jam can happen for a lot of reasons. A blood clot is one of the reasons. With a blood clot, you've got a clump of numerous red blood cells stuck together, and then those numerous red blood cells are way too wide to fit down a tiny capillary, so they're going to stuff up that capillary, and now nothing can get down. It's the same result, really, which is that downstream tissues suffocate and starve. So I don't want to tell you about sickle cell anemia. Actually, I would love to. But we just can't venture too far into pathology in this class because we have our hands full with the normal physiology. If you want to know more about it, take pathophysiology class, where we'll talk about this and lots of other pathological conditions that we just don't have time for in this class. But the presence of that picture reminds me that I want to tell you that on that hematopoiesis page, I've also given you a separate illegally photocopied story that is just a little table that is the most concise list I've ever found of several different major types of anemia. So anemias we're not going to cover. I'm never going to ask you this stuff. If you want to, you could cross it out or indicate that I'm not going to ask you this on the test. But here's what's going to happen. 6 months from now, 18 months from now, 33 months from now, it's going to be like the night before the state or national board exam. And you're going to be like, I wanted to study this, I studied it. I wanted to study this. Oh man, I wanted to study anemias. Oh, I remember that nerdy A&P guy gave me this really concise list of anemias. Look, Hemorrhagic anemia, hemolytic anemia, pernicious anemia, aplastic anemia, iron deficiency anemia, sickle cell anemia. You will not find a more concise description of the anemias than right here. You own it, use it wisely, it's not for our class. The distance to which we want to get into anemias in our class is just this. I just want you to know what anemia means, because it's too misunderstood of a word for us to let it go and not cover it here. Anemia. People seem to think that anemia means not enough red blood cells in the bloodstream. It does not mean that. In fact, it's quite possible to be anemic and have too many red blood cells in the bloodstream. Then what the heck does anemia mean? Anemia is very similar to the word we introduced tonight, hypoxemia. You know hypoxemia, not enough oxygen in the blood? Anemia is a disease, a condition, where you can't correct the hypoxemia. It's a pathological condition where you have a sustained hypoxemia, and that negative feedback system we saw with the balance beam is just not working to correct the hypoxemia. That's anemia. It's a disease process where you end up having uncorrectable hypoxemia. It's about the oxygen levels in the blood, everybody. It's not about the red blood cell numbers in the bloodstream. It's about not having enough oxygen in the bloodstream for a long period of time, despite homeostatic efforts to correct that. That's what anemia is. It's even possible that your body could be making excessive numbers of red blood cells. But for instance, if the hemoglobin is wrong, those red blood cells can't carry adequate oxygen. You could have elevated red blood cell count in the bloodstream. But if the red blood cells can't carry enough oxygen, you'd still be anemic, not having enough oxygen. So don't associate anemia with the amount of red blood cells. That's not the issue. It's about the amount of oxygen. And so I just wanted to dispel that myth, and then we'll draw a line and say, okay, we're not going further into the anemias, just to define the word. I want to be able to ask about it on our tests and quizzes, just to make sure you wouldn't go forward with a misunderstanding. Well then, where are we going from here? It says it's 7:38. Oh, well, I want to tell you a little bit more about the platelets, those little cell fragments that are involved in sealing small tears in blood vessels. You know, platelets, blood clotting. Platelets. Check out with me, if you would, figure 17 point. There it is, 17.12. This looks like that picture that led us to the red blood cells earlier, except this is not that picture. Look, all the way over to the right, those aren't red blood cells, those are platelets. This is the piece of hematopoiesis that leads to platelet development. Right? It's this pathway from the hemocytoblast stem cell to the myeloid stem cell and now to the platelets. It's that little piece of hematopoiesis, the production of platelets, everybody. Well, again, as we did with the red blood cells, there's two stages I wish we could wedge in between the myeloid stem cell and the platelets. Not that there's room to do that. I know there's not really room to do that here, so we'll make our list up here. But when we go to the textbook's version of it, again, they have left out the myeloid stem cell. See, there's somebody who just doesn't believe in the myeloid stem cell work on it. See, it worries me that people are on drugs with that problem. The hemocytoblast stem cell, as you already know from our baby book picture, first has to become a myeloid stem cell. And then I want you to see that it's going to become a cell called a megakaryoblast, which is then going to become a cell called a megakaryocyte. Platelets, we've said repeatedly, are cell fragments. They're fragments of a cell found in the bone marrow called the megakaryocyte. But I want you to know from your expert A&P 1 class that you took that if we're in a connective tissue and there's a cell called a site, there must have been some previous developmental stage where it was called a blast. Everybody get it now? We said it again tonight. So megakaryocytes came from megakaryoblasts. Where do megakaryoblast come from? Oh, myeloid stem cells can turn into megakaryoblasts. So the hemocytoblast stem cell becomes a myeloid stem cell. And then that myeloid stem cell becomes a megakaryoblast that matures into a megakaryocyte. And then that megakaryocyte buds off these little tiny fragments, these little pods, just a little bit of cytoplasm with a little bit of membrane around it, called a platelet. Don't count it as a cell. It's a cell fragment. This megakaryocyte cell should only be in your bone marrow. It shouldn't be out in your bloodstream. So what comes out of the bone marrow then is just these platelets. Not much to it, right? Megakaryoblast, megakaryocyte. It's just a big fancy scary word, megakaryo. But we know the blast and the site pattern. And we don't have to know these like separate stages. So we just combine two of them because they're both called megakaryocytes. We don't have to break it down further than that.
You won't find platelets in your bone marrow?
I wouldn't say that. I would say the other way around. That you shouldn't find megakaryocytes out in the blood. But the platelets are coming off of the megakaryocyte in the bone marrow, so you should find them in there. Of course, they're not doing their work in there. They have to leave there to go out into the bloodstream to do their work out in your blood vessels, where they help seal tears in blood vessel walls. So I wouldn't say you don't find platelets in the bone marrow. You do. Look, this process you're seeing here, the forming of this platelet, and the forming of this and this platelet and this one, this is happening in the bone marrow. Platelets are there, but then once they bud off of these megakaryocytes, then they do leave the bone marrow. For a short time, you'll find them within the bone marrow. What do platelets do? Well, it's time to get to figure 17.13. I guess we've sort of been avoiding it. Have we been avoiding it? Oh, we've been delaying. It's time to get to figure 7.13 and talk about blood clotting, except we'll do that after we take a quiz and a break. And then I'll talk about what
I don't know if I like this. I hope you don't go there. Coagulation.
Okay, everybody put your things away.